Hey, we're going to look at number 10 in section 4.4. This problem, we're going to find critical points C for the function f, and then we're going to apply the second derivative test, if possible, to determine whether each of these points, these critical points, corresponds to a local maximum, which they're calling C subscript max, or a minimum, C subscript min. So in the answers to this problem and achieve, you're actually going to just enter in the location, right? These values of these critical points. So it's not a XY pair, it's just the X coordinate, if you will. We're given a function of X here. So we're going to find the values of X that are critical points for this function. Those are what we're calling C. And then we're going to use the second derivative test to determine whether each of these points corresponds to a local max or min. So it's real important that you understand in this problem, we're going to apply the second derivative test. So you have to use that. And so on a quiz or test, if I'm asking you questions about that, you need to show the correct support. So we have been using in the previous section the first derivative test to find locations of maximums and minimums, and that's using a sign check on the first derivative, right? See where we have a change in sign from the first derivative, changing from positive to negative or negative to positive at a critical point to determine whether we have a local max or min. We are not doing that here. We're applying the second derivative test. So make sure you've watched the lecture video on how that works. Okay, so we're first going to find critical points. And in this problem, to apply the second derivative test, we're going to need actually critical points where the derivative is equal to 0. If the derivative is undefined, those critical points wouldn't be able to be applied in the second derivative test because we need to compute the second derivative and be able to evaluate the second derivative at those critical points. Okay, so here's our function that's given. I just rewrote it in this way. If you wanted to use the quotient rule, it just kind of makes it a little bit easier, or just whatever you do, make sure you don't forget this negative sign. It's important. I brought it up here as a negative 11 divided by this. So I could just use the quotient rule, which says the derivative of this quotient, right? The derivative of the top, well, negative 11 is a constant, so the derivative of negative 11 is 0. I wrote times the bottom, but of course 0 times this is 0. So this whole thing is 0. Okay, this whole thing is 0. Minus the top, which is negative 11. So notice it's minus negative 11. And the derivative of the bottom is just 2x minus 3, right? 2x minus 3 over the bottom squared. And so I have 0 minus a negative becomes positive 11 times the quantity 2x minus 3. And I would just leave it like this as completely factored, which is in a good form for us to find the critical point. Now, you could have also found this derivative just as a little sidebar. I could rewrite this and then use chain rule. So this would be negative 11 times x squared minus 3x plus 16 to the negative 1 power. So I could write it that way. And then you just have chain rule. Negative 11 is a constant multiple. So here you have u to the negative 1, where u is x squared minus 3x plus 16. So the chain rule says derivative of the outer function, u to the negative 1 is negative 1, u to the subtract 1 from negative 1 is negative 2 power, times the derivative of the inner function, which again is 2x minus 3. And so I'll have negative times negative, positive 11. I'll bring that 2x minus 3 here, times x squared minus 3x plus 16 to the negative 2 power. Well, this x squared minus 3x plus 16 to the negative 2 power is 1 divided by x squared minus 3x plus 16 to the positive 2 power. So if I rewrite that, it's exactly the same thing. Okay, so either way works, whatever you feel most comfortable with, but you've got to be careful to get the correct derivative, obviously, because now we're going to find critical points. So when is this derivative right here? When is this derivative right here equal to 0? Okay, first of all, just a note about if the denominator were 0, we would be undefined. We don't have to worry about that because that's not in the domain of the original function. In fact, this function's domain is all real numbers, because this denominator, x squared minus 3x plus 16, is always positive for any value of x. If you were to graph x squared minus 3x plus 16, it's a parabola opening upward and the vertex is above the x-axis. So there's the domain is all real numbers. So we don't have to worry about that. The point is we're looking for when the derivative is 0. That's going to be when the top is 0, right? 0 divided by some number is 0. So when is the top 0? Well, clearly when 2x minus 3 is 0. And so that's going to be true, right? When x is 3 halves or 1.5. I'm going to leave it as 3 halves because in the instructions, right? Be careful, read all the instructions. They give a lot. They want you to use fractions where you have them. So we're going to use 3 halves here. Okay, now the second derivative test, I've just abbreviated that SDT, of course, involves finding the second derivative. So how are you going to find the second derivative? Well, it gets a little messy. I'm going to actually use the quotient rule. All right, the second derivative is the derivative of the first derivative. So what if I take the derivative of the top? Well, notice the top is 11, it's constant multiple. What's the derivative of 2x minus 3? It's just 2. 11 times 2 is 22. So the derivative of the top is 22 times the bottom, which is, x squared minus 3x plus 16 all squared, minus the top, which is 11 times the quantity 2x minus 3. So that's right here. And then times the derivative of the bottom. So notice I've got a chain rule, the u squared. So the inner function u, x squared minus 3x plus 16, outer function u squared. Derivative of u squared is 2 times u, where u is that inner function, times the derivative of the inner function, derivative of x squared minus 3x plus 16, again, is 2x minus 3. So there's the top, all over the bottom squared. So if I square x squared minus 3x plus 16 squared, I get x squared minus 3x plus 16 to the 4th, right? Multiply the exponents. Now, just as a little note here, there is a common factor of x squared minus 3x plus 16 in this term right here. There's 2 of them, right? X squared, and in this term here. All right, so this minus sign separates this term from this term. So this is dividing both of these. So I can divide numerator and denominator by x squared minus 3x plus 16. That gets rid of one of these. That gets rid of this one and gets rid of one of these, right? So if I divide top and bottom by that, it simplifies down to just this. And here I did 11 times 2. 11 times 2 is the 22. And then 2x minus 3 times 2x minus 3 is 2x minus 3 squared. So now you could distribute the 22 through here, FOIL this out, distribute the 22, combine like terms, you don't want to cube this for sure. But I mean, we're not looking for anything in terms of when is this 0 or anything. We're just going to plug in. Second derivative test says to evaluate the critical points, the points where the derivative is equal to 0. And based on what you get, we can determine whether we have a maximum or minimum. Okay. And so all I'm going to do here, if I'm, doing this problem, is I'm just going to use my calculator. I'm going to enter that expression in here into my calculator. And here I just factored the 22 out first of all, factor the 22 out, and I'm left with x squared minus 3x plus 16 minus the quantity 2x minus 3 squared. Notice I put all of that in parentheses around the numerator. And then if I scroll over, so you will see it's divided by, and then in parentheses, all that to the 3rd power down here. So I can do that, and then I can go to the table, for instance, and plug in 3 halves is 1.5, and I get the value of 0.1164. Important thing is this is positive. So what does this tell us from the second derivative test? Well, it implies that f of 3 halves is a local minimum. So you need to watch the lecture videos for why that's true, but essentially here it is. If the second derivative on this interval is positive, it means the function is concave upward. If we're concave upward, we look something like this, right? Derivative as we move from left to right is increasing all the way. But we know at the point we're looking at 3 halves, we know the derivative is equal to 0. Well, where on this graph is the derivative equal to 0? Well, the answer is right at the bottom. It's where they have a horizontal tangent line. So that's where we are. Where are we? We're a local minimum. We're at the bottom of the bowl. Okay. So we have a local minimum there. Okay. There's only one critical point to check. So that's it. So the Cmax, is there a critical point that gives us a local maximum? Answer no. So the instructions say write DNE. So make sure you read the instructions. They tell you what to enter if there are no critical points for that maximum, and there is not. Cmin is, of course, 3 halves. because we know at 3/2 we get we have a local minimum. Okay, so that's how the second derivative test support should look. Okay, and so you want to make sure you understand the difference between the second derivative test and the first derivative test. They are essentially doing the same thing, although the second derivative test, right, can fail, right? In other words, if I were to find the second derivative and the value is 0, then the second derivative test is inconclusive. Then we'd have to go back to something like the first derivative test then to check to see whether we have a local max or a local minimum. Okay, so real important here. Hope you understand this. If you have questions, please let me know.